Okay, so in the previous session of analog electronics, we have discussed about the basics, ideal as well as practical characteristics of operational amplifier. Right? Now, what we are going to do is we will see some typical applications of this operational amplifier, like using op amp. What are the possible circuitries that can be designed? How to design this circuit and how to analyze this particular circuit. Okay. So as we know that the op-amp IC 741, which is manufactured by number of companies, are used as an operational amplifier. Right. So today we will see one typical concept of operational amplifier working in open loop configuration and closed loop configurations, whether open loop is advantageous or closed loop is advantageous, and we will be seeing some assumptions which is made whenever we are using the operational amplifier, right? And then we will look at the commercial IC 741 and its commercial parameters available to us. Okay, so talking about the open loop configuration first. Okay, this is the simplest possible way to use an open, that is in open loop configuration, right? So in open loop configuration, we have one inverting terminal, we have one non-inverting terminal. Okay, so we will be providing some input voltages to this inverting and non-inverting terminals. Okay, like at this non-inverting terminal, I am providing input voltage signal V1, right? And let us say at the inverting terminal, we are providing some input voltage V2. Okay, now what is going to happen? This is my open loop configuration, right? So we will be getting some output voltage V0 over here. Okay. So apart from this, we have some positive and negative supply voltage, that's positive VCC and negative VE, that is to be applied to op amp, right? So what will happen? My output will vary linearly between these two voltages, plus VCC and negative VE. Okay, as we know that in open loop configuration, gain is very large, almost infinite in case of ideal operational amplifier, and for practical amplifier also it is very much large. So what is going to happen to output voltage? Output voltage will be either at positive saturation voltage, that is plus Vset, or it will be at negative saturation voltage, negative Vset, depending on the magnitude of this V1 and V2. Okay, so if V1 is greater than V2, if V1 is greater than V2, what will happen to output voltage V0? V0 will be positive Vset, and if V2 is greater than V1, then output voltage will be negative maximum, that is negative V set. And this is, we already have seen in voltage transfer curve of operational amplifier, right? So what we have seen is VD, this is the difference voltage, that is V1 minus V2, and this is V0. Okay, so if I consider very small range of input voltage, say A and B, okay, so within this limit only my input will increase linearly with respect to output. Okay, so this is the linear range of output voltage. After that, what is going to happen? Output voltage is going to saturate between these two values, negative V saturation voltage and positive V saturation voltage, right? So this is the linear range of operation. Okay, now you can see we have already seen that this voltage is very much small. Okay, suppose we are not applying the input voltage at all, at that time also very small noise voltage which is present at the input will also get amplified due to its high open loop gain. Okay, and our op amp will get saturated. This is called saturation of operational amplifier. Remember, right? Now here from this figure, you can see only for small range of input voltage, it behaves linearly. Okay, and this range is very small, and practically due to very high open loop gain, this op amp shows either plus reset or negative reset level. Okay, and this indicates the inability of operational amplifier to work as a linear signal amplifier in open loop mode. Okay, so we have this disadvantage, that is inability of op amp to work as a linear small signal amplifier in open loop configuration, right? So the open is generally not used in the open loop configuration. Okay, and such an open loop behavior of this operational amplifier finds very rare applications. Like you can see, we will be using this operational amplifier in voltage comparator, in zero crossing detector circuits, etc. Okay, so we'll see some of the applications in open loop mode of the operational amplifier, but most of the applications are using closed loop configuration. Okay, so it is necessary to understand the closed loop operation of op amp. Okay, so we'll see closed loop operation of operational amplifier. So we already have seen before that op amp cannot operate linearly in open loop mode. Okay, but the utility of an operational amplifier can be considerably increased by operating it in closed loop mode. Okay, and closed loop operation is possible with the help of feedback. Okay, this feedback will allow to feed some part of the output back to the input terminals. Okay, so generally what happens in linear applications, this op amp is always used with negative feedback. Okay, and this negative feedback will help in controlling gain, which otherwise drives the op amp out of its linear range, even for a very small noise voltage at the input terminals. Okay, so the negative feedback is possible by adding one simple resistor. Okay, we already have seen this configuration. Okay, so now suppose we have one operational amplifier. Okay, this is my operational amplifier. We are getting some output voltage V0 over here, and there are two input terminals, inverting input and non-inverting input. Now what I am doing, see, I am just providing one resistor which is called feedback resistor RF. Okay, so this resistor is feedback resistor RF, right? So this feedback is said to be negative. Now, okay, I will call this feedback as negative feedback. Why? Because this feedback resistor connects output to the inverting input terminal. You can see over here. Okay, suppose I am connecting the feedback to non-inverting terminal, then it will be called as positive feedback. Okay, so right now we have negative feedback, and we know very well how to identify whether your feedback is negative or positive. Okay, so generally we will find almost all our applications with negative feedback, because this negative feedback will help us in controlling the gain of the operational amplifier. Okay, and the gain resulting with this feedback is called now closed loop gain. Okay, so here in place of open loop gain, now we will be available with closed loop gain. Okay, and this feedback resistor RF will help us to reduce this gain. Okay, as we know, very high output gain is provided by open loop configuration. Okay, so what will happen, no matter what amount of input signal we are providing, our output will always saturate between the positive and negative saturation values. Okay, this is not true. Okay, we must control the gain provided by the operational amplifier, and by providing a simple feedback resistor, negative feedback resistors, we will be able to control this gain. Okay, now this gain is in our hand. By deciding some values of feedback resistor and other parameter, other components of the circuit, we will be able to control, or we will be able to get the desired value of closed loop gain. Okay, and as I have told you that most of the linear circuits use op amp in closed loop mode with negative feedback. Okay, this is because due to reduced gain, the output is not driven into the saturation, and the circuit will behave in a linear manner. Okay, so whatever linear relationship which we are expecting as an output of the operational amplifier, that linear relationship will be provided with the help of this negative feedback. Okay, so negative feedback is having certain advantages. Okay, we will have a look on these advantages. Okay, advantages of negative feedback. Okay, so the first and foremost advantage of negative feedback is it reduces the gain and makes it controllable. Okay, it reduces the gain and makes it controllable, right? Second parameter is it reduces the possibility of distortion. Okay, it reduces the possibility of distortion. Then talking about the bandwidth, okay, this negative feedback will help us increase the bandwidth. Okay, it increase the bandwidth. What do you mean by bandwidth? The frequency range, right? Then it will also increase the value of input resistance. Okay, this is also desirable, right? To nullify the effect of loading, we must have very high input impedance, and this negative feedback will help us increase the input impedance, as well as it will help us decrease the output impedance also, output impedance or resistance also. Okay, and apart from this, it also reduces the effect of temperature power supply on the gain of the circuit. Okay, it reduces the effect of temperature power supply on the gain of the circuit. So these are the typical advantages of negative feedback. Okay, so the countless simple circuits using one or more operational amplifier can be designed with the help of this negative feedback. And whenever we are using the negative feedback, these applications are classified as linear and non-linear type. Okay, so we will be having total two typical applications. One is linear applications of op-amp, right? Now in linear applications, what will happen? The output voltage will vary linearly with respect to input voltage. Output voltage V0 varies linearly with respect to input voltage V in. Okay, and we will find number of linear applications like inverting amplifier, non-inverting amplifier, voltage follower circuit, summing amplifier, differential amplifier, etc. Okay, so we will discuss some of these linear applications in the upcoming lectures, right? And here remember always the concept of virtual ground. Okay, this concept of virtual ground plays very important role while analyzing the various application of circuits. Okay, so this is linear applications. Similarly, we will also be available with non-linear applications. Okay, now you know what do you mean by non-linear applications very well, right? Of course, output voltage V0 will vary not linearly. Okay, that means non-linearly with respect to input voltage. Now when this thing happens, when my output voltage is varying linearly with respect to input voltage, and when my output voltage will vary non-linearly with respect to input voltage, that depends on which kind of feedback we are going to use. Okay, so generally whenever we have this negative feedback, that means the feedback resistors is connected to inverting terminal of the op amp. At that time, we will get linear applications of op amp. But whenever we providing the feedback resistor to non-inverting terminal of the operational amplifier, that means if we are using op amp in positive feedback configurations, we will be having non-linear application. Okay, so by seeing just the circuit diagram of the circuit, you will be able to know whether we are dealing with the linear applications or non-linear applications. Okay, so using this operational amplifier for designing any circuit, we must follow some simplifying assumptions which are known as realistic simplifying assumptions. Excuse me for a minute. Yeah. Okay. So here in simplifying assumptions of operational amplifier, we will make two assumptions which are realistic as well as simplify. It will simplify the analysis of operational amplifier circuit to a great extent. Okay. So the first simplifying assumption is zero input current. Okay. This is my first simplifying assumption. Okay. So the current drawn by either of the input terminals, whether it is a non-inverting terminal or inverting terminal, is equal to 0. Okay, so in practice, the current drawn by the input terminal is very small. Okay, we have seen already. It is of the order of microamperes or even nanoamperes. Okay, so this assumption of zero input current is realistic, right? So we'll always assume that we have zero input current. And second is the concept of virtual ground. Okay, now what do you mean by this virtual ground? Okay, let us try to understand. See, the virtual ground means the differential input voltage VD between the non-inverting terminal and inverting terminal is essentially zero. And this is obvious because even if the output voltage is few volt, due to large open loop gain of operational amplifier, the difference voltage Vd at the input terminal is almost zero. Okay, that is what we have seen. Say for example, I'm taking one example here. Suppose my output voltage V0 is equal to 10 volt, right? And open loop gain is equal to, consider 10 raised to 4. Now according to output voltage equation, V0 is equal to AOL times input voltage, which is difference voltage Vd. Okay, so what will be the Vd? Vd will be equal to output voltage divided by open loop gain. What is output voltage? Output voltage is 10, open loop gain is 10 raised to 4. That means 10 raised to minus 3 volt, which is 1 millivolt. Okay, so here you can see this Vd is very small, and as output open loop gain tends to infinity, the difference voltage will tends to 0. That is what we can see. Okay, as open loop gain becomes infinity, what will happen to differential voltage Vd? It becomes 0. Okay, so realistically we have assumed this difference voltage be 0, and that is the reason why Vd, which is nothing but the ratio of output voltage to the open loop gain, that is V2 or V1 minus V2, which is equal to V0 by infinity, that becomes 0. Okay, so here what happens? The difference between two input signal is equal to 0. Hence we can say the amount of voltage available at two input terminals are same. So V1 is equal to V2 in our case. Okay, so we can say that under linear range of operation, there is virtually short circuit between two input terminals. Okay, so in this sense, their voltages are same. V1 is equal to V2, and no current flows from the input terminals to the ground. Okay, now let us try to understand with this with the help of a small circuit. See, I have this input signal V1, right? Okay, now we will have a forward resistance R1 and a feedback resistance RF over here, and here I am measuring output voltage V0. Okay, so what is happened in between these two terminals? There is a short. Okay, though physically it is not short, but we will consider virtually it is short circuited. Okay, this is my input resistance, this is my feedback resistance. There will be a flow of current I like this, and because of virtual short, this I is equal to 0. Okay, this is my virtual short, right? So this is what happens. Excuse me for a minute. Yeah. Okay, so we were talking about this concept of virtual ground in an op amp. See, if I have this case, okay, this is my output voltage V0. Here we have V1 and V2, right? This is my feedback resistor RF, and here we will have some forward resistance. Okay, let us say this is my V1 and this one is R1. Okay, So there will be a current I flowing through it. Okay. Now this V2 is grounded. Okay. So there will be some potential over here, and same potential needs to be appeared over here. Okay. So the entire amount of current I will flow in this particular direction. Okay. The current which is flowing in this direction, I, this is equal to 0. And whatever voltage, whatever potential is available at VA, same potential will be available at VB. Okay, so this VA will be equal to VB and current I will be equal to 0. This is input current. Let us say IIN. Okay, so these are the two simplifying assumptions which we will be using while analyzing the operational amplifier circuit. Okay, so this is what happens. Now suppose the non-inverting terminal here is grounded like this. Okay, so by the concept of virtual short, the inverting terminal is also at ground potential. Okay, though there is no physical connection between the inverting terminal and the ground, and this is the principle of virtual ground. Okay? So voltage at non-inverting input terminal of an op-amp can be realistically assumed to be equal to the voltage at inverting input terminal. Okay, so this realistic simplifying assumptions are always used to analyze the practical op-amp applications, and we will follow certain steps. Okay, the first step is input current of the ideal op-amp is always 0. Using this, the current distribution in the circuit is obtained. That is what we have done over here. Okay, the input current we have assumed here is 0. So the entire amount of current will flow in this particular direction. Second step should be the input terminals of the op-amp are always at same potential. That is what we have considered here. VA is equal to VB. So if one terminal is grounded, the other can be treated to be virtually grounded. Okay, so here I have grounded the terminal V2. So you can assume V1 is also at ground potential. Not V1, but VA is also at ground potential. Okay, and then we are going to analyze various expressions which are already obtained by us, eliminating some unwanted variables. Okay, so the output expression in terms of input and circuit parameters will be obtained. Okay, so in analysis of different operational amplifier circuits, we will be using these two simplifying assumptions. Okay, one is the concept of virtual short, and another one is the input ground is always equal to 0. Right? Now using this thing, let us try to understand one configuration of operational amplifier which is known as ideal inverting amplifier. Ideal inverting amplifier, right? Now if you can read the name carefully, inverting amplifier, okay, that means output of such an amplifier will be inverted compared to input signal. Okay, what do you mean by inverted output signal? That means it is having a phase shift of 180° as compared to the input signal. Okay, so you can say that an amplifier which provides a phase shift of 180° between input and output is called inverting amplifier. Okay, and let us try to understand the basic circuit diagram of such inverting amplifier now. Okay, so we have one operational amplifier over here whose output we are measuring with respect to ground. Okay, like this. Okay, now I have two terminals. One is inverting terminal, another one is non-inverting terminal. Okay, now whenever we call it inverting amplifier, that means we are providing the input supply voltage to inverting terminal. Okay, so here at the inverting terminal we will be providing some supply voltage. Let us call it V in. Okay, so this is my forward resistance R1, and we will connect one feedback resistor RF over here. This is R1, this is RF. Okay, and I am grounding this non-inverting terminal. Okay, say this is my terminal A, this is my terminal B. Okay, and this is what op amp is. Okay, so this is the typical circuit of inverting amplifier. Right. Now let us talk about the currents and voltage drops across this amplifier. See, we are at this terminal. This is my input terminal. Okay, so as and when I switch on the supply voltage, what is going to happen? An amount of current I is going to flow in this particular direction, causing a drop across R1. Right. So at this terminal now there are two possibilities. One is the current will flow in this particular direction, and second one is current may flow toward this input terminal, inverting terminal. But as per our realistic assumptions, what we have assumed? We have assumed that input current is always 0. Okay, so what is going to happen? This entire amount of current I will flow in this particular direction, okay, through feedback resistor, causing a drop across the feedback resistor, and finally this current will come to the output terminal like this. Okay, so this is what the current is. Right? Now let us try to find out the different parameters of this circuit. Okay, now here the first concept, the input current is equal to 0. That is what we have seen. Now consider. Hello. Keep your mic muted. Okay. See, the second assumption is the concept of virtual ground. Okay. So as you can see, this terminal B is grounded, right? So what will happen according to concept of virtual ground? We need to consider this terminal A is also at ground, is also grounded. Okay, so node B is grounded, hence node A is also at ground potential. Okay, so what we need to assume is VB is equal to 0, hence VA will also be equal to 0. Okay, now considering this, let us try to find out the value of current I. Okay, so current I will be equal to V in minus VA divided by R1. Okay, but VA is equal to 0, so I is equal to V in divided by R1. Let us call this as equation number 1. Okay, so this is the input current I. Okay, now consider the output side. Okay, so from the output side, if we consider the direction of current I, then I is equal to, see, current I is flowing from this terminal A to terminal V0. Okay, so if I find out the current I from output side, okay, say from the output side, okay, the direction of current is from terminal A to V0. Okay, so I is equal to VA minus V0 divided by RF. Okay, but what is VA? VA is equal to 0, so I will be equal to minus V0 by RF. Okay, so this is the amount of magnitude of current I output side, and this is the magnitude of current I input side. See, magnitude of both the equations 1 and 2 is same. because the entire current I is passes through feedback resistance, as the op amp current is equal to 0, input current is equal to 0. Okay, so we can say the magnitude of equation 1 and magnitude of equation 2 is same. So we can equate these two equations. Okay, so by equating equation 1 and 2, what we will get? V in by R1, V in by R1 is equal to minus V0 by RF. Okay, this is what our equation is, right? So suppose I am taking this V0 from the right hand side of the equation to this side, left hand side. That means V in by V0 is equal to minus R1 by RF. Okay, this is what we are getting. Now if we recall our ratio, okay, what is the ratio of output voltage by input voltage? It is called gain. Okay, so gain, A, let us say AVF is my gain, so it is nothing but the ratio of output voltage to input voltage, that is V0 by V in. And what is V0 by V in? It is minus RF by R1. Okay, so this is the gain of configuration with feedback. Okay, this is the gain with feedback. Okay, so this ratio RF by R1 is nothing but the gain of amplifier, and this negative sign indicates that the polarity of output is opposite to that of input, and this is the reason why this configuration is called inverting amplifier. Okay, so if I try to find out the output voltage V0, then output voltage V0 is given by minus RF by R1 times V in. Okay, so my output voltage gets amplified by this ratio RF by R1, and this is nothing but the gain of the amplifier. Okay, so suppose I am taking RF is equal to 10 kilo ohm and R1 is equal to 1 kilo ohm, then what is gain? Gain will be equal to 10. So my output voltage will be 10 times the input voltage V in, but the direction is opposite. Okay, so if I try to draw the input and output voltage waveforms, then what we will get is, say I have a sinusoidal input voltage which is to be applied at inverting terminal of the operational amplifier, and what output we are getting, see, the magnitude of this output voltage will depend on this ratio RF by R1, right? So whatever will be the magnitude, but the shape of this output voltage would be like this. Okay, it is 180-degree out of phase with respect to input voltage. Okay, so output voltage waveform we will be getting like this. Okay, so here you can see there is an phase shift of 180-degree. Okay, so these are the waveforms of inverting amplifier. Okay, these are the waveforms of inverting amplifier. Okay, so this is how the typical IC 741 can be used to get some output voltage. Okay, so in this case output voltage we will get, but it is 180-degree out of phase. Okay, so now here you can see by selecting the proper values of this RF and R1 we will be able to control the gain. Okay, so suppose I want to amplify my input signal 10 times, then I will choose the value accordingly. If I want to amplify the same input voltage 100 times, then also it is possible by changing the value of RF and R1. Okay, so control of gain is now in our hand. Okay, and this is the advantage of negative feedback, right? So this is one typical applications of ID operational amplifier, right? Inverting amplifier. Similarly, we will get the non-inverting amplifier also, right? So before we move on with the applications of operational amplifier, we will have a look on IC741 because this is the most widely used IC. Okay, so we will see some basics of IC741 and then we will start with the linear applications of operational amplifier. Okay, so this is a very popular IC version. Okay, it is mu A 741. Okay, and it is manufactured by Fairchild Semiconductor Company. Okay, now number of other manufacturers will also produce this IC741. Okay, so if it is produced by Motorola company, then same IC741 is known as MC1741. Okay, if it is produced by National Semiconductor, then it is known as LM741. Okay, so for convenience, this widely used IC is simply called IC741. Okay, all these ICs are simply known as IC741 op-amp. Okay, so we will drop these prefixes mu A, MC1, LM1. Okay, MC741 is manufactured by Motorola. LM741 is manufactured by National Semiconductor Company. Right. Okay, then let us talk about the pin diagram. See, all we know that IC741 is 8-pin IC which is available in dual inline package. Okay, IC741 is 8-pin IC which is available in dual inline package known as DIP. Okay, so here we will go through the pin diagram of IC. See here, you will find one notch like this. Okay, at the either side of the IC. Now here there are legs. Okay, so this is 8-pin IC. So you will find 4 legs on each side of the IC. Okay. Leg number 1, 2, 3, 4. Similarly, 4 legs we will find on the opposite side of the IC, and all these IC legs are named as pin number 1, 2, 3, 4. After that we will go to the opposite side, pin number 5, 6, 7 and 8. Okay, now the question is where to start with pin number 1. Okay, so you need to concentrate on this notch provided. Okay, this notch is where our pin number 1 is situated. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 in this particular fashion. And inside this IC, what is that? There are differential amplifiers. Okay, so we have this is my inverting input terminal, this is my non-inverting input terminals, which are nothing but pin number 2. Okay, so pin number 2 is inverting input terminal, pin number 3 is non-inverting input terminal, pin number 6 is output. So output we are getting over here. Apart from this, pin number 4, which is negative supply voltage, and pin number 7, which is positive supply voltage. Okay, so these are plus VCC, this is negative VEE. Okay, pin number 2 is input 1, pin number 3 is input 2, pin number 6 is output. Okay, and we have seen pin number 4 and pin number pin number 1 and pin number 5 are used for offset. Okay, so these pins are known as offset null, pin number 1 as well as pin number 5. Okay, and the remaining pin is pin number 8, which is not available for connection. Okay, so there is no connection between this pin. Okay, so this is the typical pin diagram of IC741 operational amplifier, right? Now we have some characteristics of IC741. Okay, ideal characteristics as well as practical characteristics. Okay, so talking about the open loop gain, okay, it is symbolically represented by AOL. Okay, now we will go through two values. One is the ideal values and second one is practical value or typical value for 741 IC. So now open loop gain AL, ideal value is infinite and typical value is 2 into 10 raised to 5. Okay, then output impedance Z out will be equal to 0 for ideal value and it is around 75 ohm for IC741. If we talk about input impedance, ideally it should be infinite, but practically it is having the value of 2 mega ohm. Okay, then input offset current IIOS, it should be equal to 0 ideally, but we will get 20 nanoamperes value. Okay, similar input offset voltage VIOS, that is also should be equal to 0, but we are getting very low voltage at the output terminal, 2 millivolt typically. Then talking about the bandwidth should be infinite, but for IC741 you can use linearly up to 1 megahertz of frequency. Okay, then common mode rejection ratio for ideal operational amplifier is infinite. Okay, but practically it is 90 decibel. Talking about the slew rate should be as high as possible, so ideal value is infinite and practical value is 0.5 volt per microsecond. Okay, then input bias current IB, okay, that should be also equal to 0, but practically we will find 80 nanoamperes of value. And power supply rejection ratio, that should be equal to 0, but practically you will find 30 microvolt per volt. Okay, so these are the ideal and typical values of IC741. Now let us try to talk about the features. Features of IC. Whenever we are using IC741, at that time you will not require frequency compensation. Okay, so frequency compensation is not required. Okay, this is one of the features. Second, these IC741s are already provided with short circuit protection. Okay, so short circuit protection is provided. Then it has pin number 1 and pin number 5. So it will provide offset voltage null capability. Okay, and large common mode and differential voltage range is also one of the feature. Large common mode and differential voltage range. Okay. So these are the some of the features of IC 741. Okay. Now talking about the packages available for this operational amplifier. Okay. Whenever you will go to the market, you will ask for operational amplifier. Okay. So you will find out that these op-amps are available in different packages. Okay. First package already we have discussed. You will find out your IC in this chip type. Okay. We will be getting one small rectangle kind of piece where 4 number of pins will be on each side of the IC. Okay, so this kind of package is known as dual inline package. Okay, so the first kind of package which is available is dual inline package known as DIP. Okay, apart from this, you will find out the IC in metal cane package. Metal cane package. Okay, which is known as TO. Okay, now what you will get is you will get your IC in this particular shape. Okay. There will be a shape of metal, circular shape like this, and several number of pins. Okay. This is also 8 pin IC, pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, pin number 7, and then there will be a pin number 8. Okay, and to identify this pin number 8, we will be available with one tab. Okay, so the tab needs to be considered as pin number 8. Okay, so if you see the top edge, okay, suppose what I have operational amplifier in this case. Okay, so we will be available with this pin number 6 as output. Okay, so this will be my output pin. Then we have input pin number 2. Okay, so here we will get pin number 2. Similarly, we have pin number 3. Okay, so here I will get pin number 3. Then pin number 4, pin number 5, this is pin number 6, this is pin number 7, this is pin number 8, and pin number 1. Okay. And all these are connected with the help of a circular cane like this. Okay, so this is what the top view of metal cane package can look like. And there is one tab. Okay, so here at pin number 8, okay, this is my pin number 8, this is my pin number 7, 6, 5, 4, 3, 2, and 1. Okay, here at pin number 7 we are providing positive supply voltage, at pin number 4 we are providing negative supply voltage, pin number 6 is output, pin number 2 is inverting input, pin number 3 is non-inverting input, pin number 1 and 5 is offset null. Okay, so these are metal cane package, or you can call it TO packages. Okay, and then there is third kind of package which is available. It is known as flat package or flat pack. Flat package or flat pack, right? So talking about these three, the dual inline package. Okay, first we'll talk about the metal can package. They are available with 3, 5, 8, 10 and 12 wheels. Okay, so the metal sealing plane will be at the bottom under which is silicon chip bonded. Okay, and this plane is effective for the dissipation of heat. I am talking about this plane. Okay, this is effective for dissipation of heat. Then there is a dual inline package. Okay, this is popular for commercial applications and it is very easy to handle. Okay, it fits standard mounting hardware and it is inexpensive when it is molded in plastics, right? Then we have the flat packages. Okay, so flat packages are also available. Let us try to understand this flat package. I will be available with and shape like this. So around this, we will find out the legs which are very flat. Okay. So what you will find is the height of these ICs is very much low. Okay, we can call it surface mounted. Okay, it is mounted on surface. So the height of this kind of package is very much low. So this is one kind of ceramic flat package. And as you can see, it is a 10 pin IC. Okay, so 10 number of pins are there. Okay, so pin number 1, pin number 9 and pin number 10 will not be used. There are no connections. Okay, and pin number 2, 3, 4, 5, 6, 7, 8 will be usually supply voltage, input terminal, output terminal, etc, etc. Okay, so this surface mounted technology is used where very higher circuit density for a package of a given size is required. But remember, this is complex circuits in which many op-amp and other integrated circuits and many large chips are placed in a single package. And these packages have lower noise and improved frequency response characteristics. Okay, so we may find any TO package, dual inline package, or flat package for our ICs. Okay, so these are the packages which are available for IC 741. Okay, and there are different classes of op-amp IC like military grade, improved version. Let us try to see these versions. Okay, when we have a 741, it is having military grade. Okay, then there comes 741A. This is the improved version. Okay, it is improved version of IC 741. Then we may have 741C, which is commercial grade. Commercial grade. Then we may have 741E class, which is nothing but the improved version of commercial grade class. Okay, then you will also find the type 741S, which is again of military grade. Okay, and then 741SC, which is commercial grade. Okay, so these are the difference. See, if I talk about 741 of military grade, then it has a temperature range of minus 55 degrees Celsius to positive 125 degrees Celsius. Okay, then in an improved version of IC 741, they have better electrical characteristics. Okay, if I talk about commercial grade, then the temperature range will be around 0 to see 0 to 70 degrees Celsius, and here minus 55 to plus 125 degrees Celsius. Okay, and again in improved version of 741C we have better electrical characteristics. Okay, for this 741S we have higher value of slew rate. Okay, and in commercial grade also same, we will have higher value of slew rate. Okay, so these are the different classes of operational amplifier IC 741. Okay, so this is one typical IC which is very widely used. Okay, whenever we are going to design any analog electronic circuits, we will take this IC 741 only for our circuits. Okay, so today we have seen some realistic simplifying assumptions which are to be made for analysis of IC 741 circuits, and we have seen one typical applications as an inverting amplifier. Okay, so from next lecture we will continue with these typical applications. Okay, first we will start with the linear applications of operational amplifier, and then we will move on with the non-linear application of operational amplifier. Okay, so we will stop here. In the next lecture we will continue with these applications of operational amplifier. Okay, so here comes the end of the first module of